So we started talking about systems of numeration last time, and one of the interesting things is looking at how people thought about numbers over the course of the time that human beings have been on this planet. It gives us insight in how they think. It also gives us insight in the importance that numbers have. And so we're going to fast forward in history now a little bit to a couple of examples of what's called place value system, which were precursors to the system that we enjoy and that we use now. So this is section 4.2. And in section 4.2, we're going to talk about place value systems of numeration. Remember, a number is the how many, the numeral is the symbol that represents, and then a system of numeration is all the rules with your numbers and your numerals and how they go together. So in a place value system, now you probably know this intuitively, you just haven't spoken it and defined it out loud, but in a place value system, the value of a number, the value a numeral represents, depends on its position. Now we know this because these two numbers that I write on the board have the same numerals, but they mean entirely different things. So if I write 1, 2, 3, that means something completely different to us than 3, 1, 2, right? It's the same three numerals, but putting them in a different order communicates something completely different. And that's because of the place value. So the system that we use, I mentioned this last time, but I'm going to just tell you again. The system that we use is called the Hindu-Arabic system. Because of its historic development throughout the centuries, the Hindu-Arabic system is base 10, and that's called a decimal system. So the system that we use is base 10, and a base 10 system is called a decimal system. Now, when we come back on Wednesday, we are going to use our Hindu-Arabic numerals, and we're going to learn to think a little bit in other bases. Some example, and a great example is computers think in base 2. So we're going to look at how computers do calculations and things like that in base 2. But what it means to be a base 10 system is this. In each of my places here, the last numeral, this represents my units or my ones. So I'm just going to write the word units here. And then each successive place that I go to the left represents 10 times the previous place. So the 2 represents my 10. So instead of just being 2 units, it's now 2 tens or 20. Okay, so this represents my tens. And then I multiply again by 10, and the next one becomes my hundreds. And that's what it means to be a base 10 system, is each place is 10 times the previous place. And we could do that forever. If you had a long number, then your rightmost place is always your units, and then you would go, the next place is your tens or 10 to the first. The next place would be your 10 to the second or hundreds. Your next place would be 10 to the third, your thousands, 10 to the fourth, your 10,000s, your 10 to the fifth, your 100,000s. And I'm not going to bore you to death by keeping on doing that. But the point is that each successive place is 10 times. And that's what makes it very useful. The kind of the brilliance of the Hindu-Arabic place 10 system, place value system, is it makes calculations become very easy. All the things that we take for granted when we write down addition and subtraction and all of that took thousands of years to be able to develop. So here's what we're going to do, just to again wrap our minds around the place value system. this little thing that we're going to do will actually be a pretty good tool as part of some other problems. So don't discount its importance just because it's something that you did in middle school. Okay, so what we're going to do is we're going to take a number and we're just going to write it in expanded form. So for instance, this is example 1 on the page that I gave you. We've got 24,000, excuse me, 659. And we are just going to take this number and write it in what's called expanded form. And expanded form means we are going to take each of the place values and write them separately. So here's what I've got. I've got 20,000. So what I've got is I've got 2 times 10,000 plus, then I've got 4,000. So I've got 4 times 1,000. Then I've got 600. So I've got 6 times 100. Then I've got 50, so that's 5 times 10. And then lastly, I've got 9, and that's 9 times 1, or just 9 units. Let me write 9 times 1, because that's kind of the exercise we've got going on. I'm going to do one more thing to this expanded notation, just because I want you to be able to see the pattern, because it's going to be very important, because today and Wednesday, we are going to talk about systems that are not necessarily place 10, but they all work the same. Okay, so if you can see what's going on here with our expanded notation, you'll be able, when we talk about the Babylonian system in just a minute, which is not base 10, but you'll still be able to do the calculations if you understand how the places work. So 2 times 10,000, as you saw over there, 10,000 is 10 to the 4th power. And then 1,000 is 10 to the 3rd power, and then 6 is 10 to the 2nd, or excuse me, 100 is 10 to the 2nd, 10 is 10 to the 1st, and then 9 times 1, and 1 is just 10 times 10 to the 0 power, but I'm just going to leave it as 1. The reason we took the time to do this exercise, I just wanted to see the pattern. Nothing more than that. Notice each place, okay, my units, and then each power on the 10 gets 1 more. I've got 10 to the 1st, I've got 10 to the 2nd, I've got 10 to the 3rd, 10 to the 4th. If this was 100,000s, I got 10 to the 5th. Millions, I got 10 to the 6th. And we could do that as large as the number gets. So I would please like you just to take a moment. We're going to do this twice just because, believe it or not, being able to write something expanded form is going to be a very useful tool to you to be able to do half the problems that we're going to do in the next 2 sections. So if you would take exercise 1, 3,769, and please write that in expanded form. So what we have here is we have 3 in the thousands position. So that's 3 times 10 to the 3rd. 10 to the 3rd is my thousands position. Plus I've got 7 in the hundreds position. So that's 7 times 10 to the 2nd. Then I have 6 in the tens position. That's 6 times 10 to the 1st. And then I have 9 units again, just like the last problem. So that's 9 times 1. We okay? Everybody doing all right? Writing things in expanded form. Let's do one more, just so that we experience the joy of millions. So exercise 2 says take 3 million and the rest of it write in expanded form. Yes.
So is expanded form the one where you're doing to the power or to the thousand? They mean the same thing, or which one are we supposed to do?
Well, the one that the final answer, the one that's the expanded form, is the one with the power.
Okay.
I did the times the thousands here just to give you the relationship between where those powers came from. And if you did that as an intermediate step here, that's totally great. All right, I'm just going to start from the right edge of this. It doesn't matter if you go left or right. I'm going to start from the right edge. So my 4 is in my units place. So that is 4 times 1. And then the 3 is in the tens. So that's 3 times 10 to the first. And then the 9 is in the hundreds. So 9 times 10 to the second. So the nice thing about expanded form is I just keep increasing the power on the 10, 1 each time. So the next one is thousands. So that's 5 times 10 to the third. And then 10,000s, 6 times 10 to the fourth. And then 100,000s, so 7 times 10 to the fifth. And then last but not least, millions, 3 times 10 to the sixth. So we did expanded notation with our decimal system, which we're familiar with and used to. I'm sure at some point in your middle school math history, you had a teacher that was teaching you the place value system. The reason we do that, though, is because writing things in expanded notations is going to become for us one of our tools. So now we're going to turn our attention to one of the earliest place value systems. Okay, there were several different ones through several different cultures, but this one is the earliest known one we know about because we have clay tablets and things like that. So the oldest known place value system was used by the Babylonians. Okay, so that's the one that we are going to focus on first. The interesting thing about the Babylonians is both they and also the other culture that we talk about today were both very into the calendar. Okay, it kind of dominated their life, as you would expect, because you have to grow things. And so because of that, instead of each position representing a power of 10, the Babylonian system is base 60. And this is called a sexagesimal system, which is very fun to say and spell. So for the Babylonians, they thought not in groups of 10s like we do. They thought in groups of 60s. So remember, as we go through this and we're learning to use the Babylonian system, yes, it's going to be awkward. We're wrapping our brain. We're retraining our brain to look at things in a new way. For the Babylonians, they would have looked at numbers like we would have looked at numbers, and they would have seen their symbols, and it would have had meaning to them right away. They wouldn't have had to go through the awkwardness that we are going to have to as we are learning to use it. Now, notice that one of the nice things for us is the Babylonians had 2 numerals. Okay, you can see them there, that they were formed using the end of a reed in clay. And so the 1 was just they took the reed and they stuck it straight down. And then the 10 is they took the reed and stuck it and then kind of curled it around to make that V-looking symbol. So those are their 2 numerals. They had a numeral for 1 and a numeral for 10, and they used those to write their numbers. So example 2 that we're going to do together, we are going to take this number right here. I am not a super artist, so work with me. Somehow my brain can't make my hand do what it needs to do. We are going to take this Babylonian number and we are going to convert it into our Hindu-Arabic system of numeration. So here we've got 10, 20, 1, 2, 3 of this place value, and here we've got 10, 20, 1, 2, 22 of this place value. Remember, the Babylonian system is a base 60 system. So I'm going to come over here, and I'm going to write out what the places would mean for us, okay, in our Hindu-Arabic way of thinking. So the rightmost place is going to be units, okay, just like we like to think about it. But then instead of every place being 10 times the previous one, every place is going to be 60 times the previous one. So after the units, instead of 10s, you would have 60s. And then it's not going to apply to this problem, but it'll apply to a future problem. The next, instead of 60s, would be 60 to the seconds. And that's probably as far as we'll go with the Babylonian system. But if you kept going, the next place value would be groups of 60 to the third. So hopefully by doing expanded notation with our system, this gives you a little bit of a feel for what's going on. So in the sexagesimal system, each place is 60 times the previous place, and that's how they thought about numbers. So what we're going to do, and this is the note down at the bottom of page 1, when we convert another base to base 10, whether it's the Babylonian base 60 or when we come back next time and we're doing computer base 2 or computer base 16, when we're taking another base and converting it to Hindu Arabic, we are going to use expanded notation. That's why we practiced it. And what I mean by that is this, okay? So this is, according to the symbols, this is 10, 20, 1, 2. So I've got 22 units, so 22 times 1, plus, it's the same thing that we were just doing with those base 10 numbers, okay, doing that practice. Then here I've got 10, 20, 1, 2, 3, so I've got 23, but now I'm in the next place over, and it's 23 groups of 60. One thing about the Babylonian system, and I'm not going to quiz you on this, I'm not going to make your life difficult. It wasn't until later Babylonian writings, like 1,000 years in, that they started to realize they needed a placeholder, they needed a 0. 0 was very slow to develop in the history of human thought, okay? Because again, I mentioned this last time, if you didn't have anything, you didn't need to count it. But the Babylonians began to realize, oh, how do I know that this is not 60 to the second or 60 to the third? How do I know it's 60 if I don't have something? So later on in their writing, they would use a dot if they were skipping a place. You don't need to write this down. You don't need to know this. I'm just letting you know that the idea of having a 0 took time in order to develop. So now you're just going to use your calculator to figure the rest of this out. 22 times 1 is 22. 23 times 60, I don't know, it's still a little too early in the day to go ahead and do that without our good friend the calculator. So 23 times 60 turns out to be 1,380. And when I add those two things together, I get 1,402. So remember, this is something we talked about last time. The number is the same. We think about it like this, 1,402, that has meaning to us as far as size and scope. The Babylonians would have represented that same number this way, and they would have looked at these digits the same way we look at these digits. That would have had meaning, and they would have known, you know, this is bigger or smaller than they expected, or whatever the context was that they were using it. Different way of thinking. Flip to the next page, please, in your little packet. And so you have another 2-digit number right there that you are going to do. Very similar sort of thing as this. Write that number as a Hindu Arabic number, please. For this problem, my units place, I've got 1, 2, 3, 4. So I've got 4 units plus, then I have 10, 11, 12, 13 of my groups of 60. The next problem that we do together is going to have 3 places. So I just want to mention it now. The third place, if we had anything here, would be not 60, but it would be 60 to the second. It would be 60 times this one. Each place value would be 60 times the previous one. So again, we could use our calculator. 13 times 60. What's 13 times 60? 780? 780 plus 4 is 784. That's how we would represent that number. This is how the Babylonians would represent the number. Are we doing okay? All right, good, because this is, I understand, this is difficult stuff. It's awkward to think differently. If you can do this for the Babylonian system, by the way, then you can do it for any of the other systems, okay? We're going to be repeating the same two processes for these different place value systems. Okay, so we're going to do another one. This one I'm going to do along with you. This is example 3. There is one other thing the Babylonians had in their toolbox. Okay, so this is the next number. It's got three places. Now notice in the units place, we've got a new symbol. What this symbol right here means is it's a way, it's kind of like what the Romans did as a way to write fewer things down. This means subtract. So you take whatever's on the left and you subtract from it what's on the right. Given that, what do you think? Okay, here's the hypothesis. What do you think it's representing when I have these two symbols over here, subtract these two symbols? How many units do I have? 18. Okay. Unlike the Romans, I know this question was asked in class last time. Somebody wanted to write something like XXL for 30. And I told you in the Roman system, that would have made no sense. They would only, whatever the one smaller number right before the larger, that's what. But for the Babylonians, it's whatever's on the left, 20, minus whatever's on the right, 2. So that becomes 18. So if you were wondering where the 18 came from. So I have 18 units. And then we have 11 groups of 60, just like the previous problem. And then this time we have 2. And what is the place value for this one right here going to be? 60 squared or 3,600. Yes, you've just done the multiplication, but I'm going to let my calculator do that. But exactly. Perfect. Anybody bothered by the 60 squared here? We doing okay? Okay, so 60 squared is 3,600 times 2. I think that's 7,200, but you should always check me. And then 11 times 60 is 660. And then 18 times 1 is 18. And then when we add those three numbers up, we get the final value. And that's going to be 7878. We're going to do one more of these, and then we're going to say, let's reverse the process. What if I give you a Hindu-Arabic number, and we're going to write it in Babylonian base 60. But before we do that, do exercise 4, please. All right, we've got the subtraction symbol here. What does this represent? How many units do I have? 8. It's 10 minus 2, so that's 8 units. And then 10, 21 groups of 60. And then finally, one group of 60 squared or 3,600. So 1 times 60 squared is 3,600. 21 times 60, what is that going to be? 1260, I'm going to go with that, plus 8. And when I add these three values up, what do we end up with? 4868, did I hear you right? Somehow we got this giant wind blowing in the room right now, so I can barely hear anything. Okay, are we doing okay starting with the Babylonian base 60 and putting it into our way of seeing numbers? Okay, we're going to do this over and over. We're going to do this in a moment for another culture's numbers. When we come back next time, we're going to do this for just different bases because bases have different usefulnesses, which I don't even think that's a word. Probably should just say uses, but I don't know. But now the other process we're going to do is we're going to reverse it. We're going to start off with a number we would recognize, and we're going to write this as Babylonian. So what we're going to do in example 4 is just that. Example 4 says take 2,519, and we're going to write that as a Babylonian number. Now, in the note that I have for you below this problem, the way we're going to do this, no matter what base we're converting to, we're converting to base 60 now, but when we come back and we're working in base 4 or base 5 next time, you're going to do the exact same thing. These processes are not going to change. Okay, so once you catch on to them today, it's going to be the same thing. What we're going to do to convert base 10 to another base, we are going to regroup using the new place values. Okay, so the word for the blank is we're going to regroup. So an additional note you might make is what I would recommend when I'm asking you to write something Hindu Arabic into another base, the first thing I would have you do is let's list the place values. We're going to list the place values. So for Babylonian, that is, we start with our units. And then the next, I'm just listing them up and down instead of left and right, just because I'm going to keep them in the middle of the board. It saves me a little room. Then my next place value is groups of 60. And then what's the next place value? 60 squared. The units are at the bottom, then my 60 is my 60 squared, which I was already told is 3,600. Let's go one more just to make sure we're catching on. What would the next place value represent? 60 cubed, and that's going to be a large number. That's going to have 3 zeros at the end of it, and then 6, carry the 3. What? Yep, great. So notice with the Babylonian system, their numbers get big really fast, right? Their places, they're already on the fourth place, and you're up to 216,000 of whatever you're counting or grouping. Okay, so here's how you do this then. I'm going to take this base 10 number. I want to write it in Babylonian. So I'm going to start with the largest base that the largest place that I can divide into 2,519. So can I divide 60 into 2,519? Does 60 go in? We'll have some remainder, but I can divide 60 in. Would you say that? Can I divide 3,600 into 2,519? No, the place is too big. Okay, I do not have enough things that I'm counting to make a full 60 squared. Okay, so where we're going to start on this one is groups of 60. So here we go. I'm going to take 60 and I'm going to divide it into 2,519. I'm just going to go old school division because I don't need decimals. I'm just interested in remainders. So here we go. 60 goes into 251 4 times. 4 times 60 is 240. Do my subtraction, and I'm left with 11. Now I'm going to bring the 9 down. 60 goes into 119. Looks like that's going to happen once. 1 times 60 is 60. And I'm left with 59. So now I'm going to go over to my list of the place values, and what I've just seen is that I have 60 went into 2,519 41 times. And now the only other thing is my units. So what's left over, my remainder, I don't have anything else to divide into. The remainder becomes my units. So we have 41 groups of 60, and we have 59 units left over. So then the very last part is, okay, that's great. Now I've got to write that as a Babylonian would. So I'm going to ask you to get your clay tablet out of your bag and your papyrus reed, and we're going to write this down. So since we don't have that, we're going to pretend. So 41, we're going to write as, oops, that's not what I meant to write. We're going to write as 10, 20, 30, 40, 1. That's 41, groups of 60. Then I'm going to leave a little space. Now, I do not know the Babylonian rules for subtraction. Okay, so I don't know when they would or would not use it. So I'm not going to be fussy on the test. Okay, as long as you represent 59 in some representative way. I will use the subtraction here because it will be a little bit quicker, but I won't mark you wrong if you don't use the subtraction. So for 59, I'm going to do 10, 20, 30. You can see that my 10s get progressively worse. 50, and then 60, and then at some point it just even looks like I'm not even trying anymore. Then I'm going to subtract 1, and so there's my 1. So I know this is difficult stuff, and we're going to practice it a couple times. But the essence of it is to take a place 10 number and write it in another base. We have to do the regrouping. So step 1 is we list out what the places mean. And then we start with the largest place value we can divide into our number. And in this case, it was 60. Here's yours. It's going to be very similar to what I just did. You're going to do the number 5,363. So notice you're going to be able to start one place more because for 5,363, you can divide 3,600 into that. It's going to go one time. So you're going to start with that, and then you're going to work down your places. Give it a try. If you don't quite get it, it's okay. We are going to do several more. It's a learning process. All right, so you might not be done, I'm gonna get started because the next two problems are just gonna be a repeat of this so that you can get used to the process. So 5,363, we want to convert this to Babylonian base 60. So I've listed out the place values of my Babylonian system here. I've got units, I've got 60s, I've got 60 squareds, which is 3,600, 60 cubes, which is 216,000, and then we could go up and up and up, but there's absolutely no need to. So we notice this time I can start here because 3,600 does divide into this. So 3,600 does divide into 5,363. And it is going to go in one time. So when I subtract, I've got 3, I've got 6, and then I got to borrow here. So I've got 7. 1763 is what's left. Are you tracking with me? We okay so far? Because I'm going to leave this work up here because it's going to be identical work to when we do the next problem, which is 7,223. It's going to be very similar. So far, in my Babylonian number, I've got one group of 60 squared. Now, I'm hoping you figured this out, but just in case you didn't, what am I going to now do with this remainder, this 1,763? How many groups of 60 is that? Great. I liked the universality of your voices. That was nice. If you didn't quite get that, that's okay. There's no shame in that. We are learning. So now I'm going to see how many groups of 60 that is. So 60 goes into 176. It looks like that's going to happen, what, twice? So that's 120. Leaves me a remainder of 56. I'm going to now bring down the 3. And 60 goes into 563. Well, 9 times 6 is 54. So that leaves me 23. So that means, as you said, we divided in to see how many groups of 60, and that was 29. And then I don't have any other places to divide into that. So that means those 23 things are my units. We doing okay? And then the last challenge is to write this Babylonian. So I'm just going to start with my largest. Hey, I've got one group of 60 squared. So there we go. I've got 29 groups of 60. So I'm going to write that as 10, 20, 30, minus 1. And then 23 units. So I've got 10, 20, 1, 2, 3. Questions?
How do you represent 0 for exercises 6 and 7?
If there is a 0, just skip the place. You don't have to do anything. Okay, so like if you were an archaeologist reading Babylonian, it would be, at first they had to learn, it was just a matter of context.
Okay.
But that's why later in their empire, they started using a dot to represent, oh, we're skipping a place here to make it easier to do. Okay, but you don't need to know that. Okay. You just, if it does end up having a 0, you just skip over it. Any other questions? Lovely question. All right, we'll give the next one a try. Okay, we're just going to do this a couple more times because I know this is a very difficult thing. You are learning to think in a brand new way. 7,223.
We had the base 10 decimal system. How come it took us so long to develop the metric system, and why do we not use it in the States?
Well, people are just resistant to change, right? So the reason it takes a while to learn to have new things is because the old things are kind of working for you. And it's, as you're learning, it takes time to learn something new and use it. Why don't we use it in the United States? Because we're very stubborn people. That's why. In the 70s, they tried to convert, and there's some funny stories that if you go back and look, like when they would change the speed limits, instead of being 50 miles an hour. And we're going to do 6 times that. So 80 kilometers per hour. People complain because now they are going too fast. They didn't have that fast, right? So
it's like when they had the third pounder and people didn't buy it, they thought it was less than a quarter pounder.
that's middle school. Middle school. I lost. So okay. So next problem, I'm going to come over and we're going to run through and see where you're getting hung up. Okay. So let me work this one and then we'll try the next one. Okay, so again, I'm converting this to Babylonian base 60. Anytime we convert to a new base, whether it's 60 or when we get to the next one or whether we're doing base 4, we are going to regroup using new place values. So here are the Babylonian place values. And so we notice this time I can start with 60 squared again, or 3,600. And so 3,600 divides into 7,223. And then 36 times 2 is 72. So that's why I'm going to say 2 times 2 times 0 is 0. 2 times 0 is 0. 2 times 6 is 12. And then 6 plus 1 is 7. And then I have 23 left over. So I have sorry, that is wrong. I have 2 groups of 3,600. And then here is the relevance of the question that was asked before the problem is I only have 23 left. So how many groups of 60 do I have? 0. There's not enough to make a full group of 60. So this was a little less division than the previous problem. And then I have 23 units left. So I have 2 60 squareds. So 1, 2. If you want to put a little dot in there, I meant to bring my handout about the historical origins of the number 0, but I forgot it. And then I'm just going to skip a space and we have 10. Whoops, no, we don't. Here we go, 10. I think it's just because I don't want to draw this thing anymore. 10, 20, 1, 2, 3. There we go. That's how we'll represent that. All right, one more of these just to practice the process. And then we'll go a little bit quicker through the next place value system because the processes are going to be the same. It's just a matter of learning the new place values. So if you could do 9,345. So we need to know how many times is 600 going to go over there. So that's still less than that. 10 times 3. So that's going to be 2 much. Now we can multiply. So 2 times 0. 2 times 0. 2 times 6. 2 there. 2 times 3 is now you just subtract. You need to calculate 1,245. So now what's left is that. So now you just figure out how many 60 squares there is. So now I'm going to put the 20. What's the next first value? So we just do 3,600 to 60 squares. So what are we going to find next? So now we need to do that. Okay. Now do the same thing, just to see 60 times what's going to get you close to that. I'm glad you asked. All right, just for time's sake, because I want to make sure that we adequately do the other system for the day. So we started off with 9,345. We noticed that the 60 squared, which is 3,600, I can divide into that. It goes 2 times 3,600 is 7,200. You can subtract and you get 2145. So what way we start out is we have 2 groups of 60 squareds. Now I'm going to divide the 60s. I'm just going down the ladder there. We divide the 60s into 2145, and it goes 35 times. 3 times 60 is 180. And when I subtract the 214 and the 180, that leaves me 34. And then I bring down the 5. 5 times 60 is 300, leaves me 45. So what that means is I have 35 of these and then 45 units at the very end. And then the last challenge is to write it Babylonian. We doing okay? Okay, please let me know. So there's the 2 groups of 3,600. And then I've got 30. Doesn't really seem like there's going to be any advantage to subtracting. So there's 35 groups of 60 and then 45 groups of units. And there we go. All right, we're going to keep practicing these processes. So it's not going to go away. So we're going to flip to the next page. Another example of a group of people who were excellent mathematicians and had a very accurate calendar. They are the Mayans. So another example is the Mayan system. Now the Mayan system is an almost base 20 system. Okay, it would be a little easier if everything was just base 20. But the reason that they made one little twist to the system instead of being straight base 20 is because of their calendar, which they were really good at reckoning. So good was the Mayan calendar. I don't know if this happened before any of you had awareness, if you were just toddlers at the time, but the Mayan, they had their calendar on a big rock, and it stopped at the year, I think, was it 2012? You remember more than me. At 2012, their calendar stopped, and because it stopped because they ran out of room, okay? But because the calendar was so good, the rumor came that it was going to be the end of the world on whatever day on 2012. And so it was people really just want the end of the world, apparently. Okay, so the Mayan system goes like this. Okay, these are the Mayan place values. This will be the most difficult part of the Mayan system. And in fact, of all the systems, we'll talk about the Mayan, I think the Babylonian one's pretty straightforward. Everything's base 60. When we come back next time, all the place value systems are going to be nice, straightforward. Here is the Mayan place values. Okay, we got units just like the Babylonian system. And then it's primarily base 20. So after that, their next grouping are going to be groups of 20. Now here's what you would expect. Don't write this down. If the Mayan system was a straight base 20 system, then the next thing would be groups of 20 squared, and the next thing would be groups of 20 to the third, on and on and on. But that's not what they did. Their next place value, again, because of the calendar, their next place value is not 20 times 20. They made it 18 times 20. Because what's 18 times 20? 360. Their calendar had 360 days. So that's how intertwined their thinking was with their calendar. So 18 times 20 became 360. So instead of multiplying here by 20 like a straight base 20 system, they multiply by 18 to get 3. From there on, though, then they just keep multiplying by 20. So the next one's going to be 18 times 20 squared. We'll calculate that in a minute. The next one's going to be 18 times 20 to the third. From then on out, they keep multiplying by 20. It's just that one place that makes all the difference. So what's 20 squared? 20 times 20 is 400. Times 18 turns out to be, anybody have their calculator handy? 7,200. I'm just doing this for our groupings later. 20 to the third power, so that's 400, so that's what, 8,000. So 8,000 times 18 is going to be 100 what? 144,000? Thank you very much. And that's going to be adequate for our purposes, but you could keep multiplying by 20 over and over again and continue on. So I've given you the symbols. Remember, I told you last time, I'm always going to give you the charts. You don't have to remember the, I mean, even though actually the Mayan one is probably the most intuitive one. A dot represents 1, a line represents 5. But you don't have to remember that. I'm going to give you that. What you have to remember is how to work with the Mayan system. And the other interesting thing about the Mayans, I wish I knew some archaeology or anything like that. They write their numbers like the traditional Chinese. They write top to bottom. So it's just interesting if there was like some sort of mingling of those cultures. Anyway, that's just something I think about. So what we're going to do is we are going to write this number here as a Hindu-Arabic number. Oh, the other thing I want to mention, the Mayans, again, because they were super advanced, the Mayans have a very clearly defined 0. They use an empty basket for 0. So you'll notice that as we go through, that when there's nothing in a particular place, they use the empty basket. Okay, so remember, when we convert another base to base 10, we use expanded notation. Okay, so we are just going to use expanded notation on this, remembering that the bottom are my units, these are my groups of 20, these are my groups of 18 times 20. So here goes. I'm just going to do this top to bottom like the number is written. I've got 5, 10, 11 units. I'm using expanded notation here. To convert to Hindu-Arabic, this is the note on the bottom of the first page. To convert to Hindu-Arabic, we always use expanded notation. Then I have 3 groups. Oh, it has 3 lines? All right. If you want to be a stickler for details. So that's 16 instead of 11. Sorry about that. So the next one is 3 dots. So that's 3 times 20. That's 3 groups of 20. And then the top place, this is the one little twist to the Mayan system you have to remember. I've got 11, and that's 11 groups of 18 times 20, or 360. So what that's going to equal then, 16 times 1 is 16, 3 times 20 is 60, 11 times 360, what is that, 3,960? Yes? Just got lucky. So then we have 6 and 13, carry the 1, and then 4,036. Please do exercise 8. There's another Mayan number at exercise 8, and you are going to write it as a number we would understand, Hindu-Arabic. Notice the empty basket. All right, so I'm just gonna do this, then we have one more, just to make sure. Again, it's the same process we used for the Babylonians, it's just different place values. That's the thing that you have to remember here. So at the bottom of my number, I have 4 dots, so that's 4 units, 4 groups of 1. Then I have an empty basket, so that's 0 groups of 20. And then I have 5, 6, 7, 8. So I have 8. And now remember, this is the interesting twist on the Mayan system. This is groups of 18 times 20 or 360. And then last but not least, we go up to the next one. I have 2 groups of 18 times 20 squared or 7,200. So then just going to go ahead and get my calculator fired up here. So 2 times 7,200, just so that I stay on the video, I'm going to write my numbers down here. I apologize for not using my space well. So the top number is 14,400. 8 times 360 is 2,880. 0 times 20 is 0. 4 times 1 is 4. And when I add all those up, what do we end up with here? 17,284. We would think of the number this way, the Mayans would think of the number that way, but it's the same number that's being represented. Question? See a couple of discerning looks there. Let me know. Speak if you need to speak. Otherwise, go ahead and do the last one on page 3. We're going to take one more Mayan number and write it in Hindu Arabic. All right, so the bottom one is 5, 6, 7, so that's 7 units. The next one is 5, 6, 7, 8, 9. It's 9 groups of 20. The top one is 7, and that's 7 groups of 360. Again, that is the novel thing to the Mayan system, is they don't go straight base 20. And I go ahead and multiply these things together and come up with my answer. 7 times 1, I can do that one. And then 9 times 20 is 180. And then 7 times 360, 2,520. Perfect. And when I add those up, we have 2,707. Great. All right, so we have just a couple more examples. I'm going to do one more. You're going to do 1 or 2 more, just depending on what time allows. So again, now we're going to start with a Hindu Arabic number. We're going to write it in a different base. In this case, Mayan base sort of 20. So just as I mentioned with the Babylonians, this is the process of regrouping. So the first example, example 6 at the very top of the last page, says we are going to start with the number 4,025, and we're going to write this as a Mayan number. Well, which place am I going to start with? What is the highest place value that I can divide into 4,025? 360. Okay, this place right here is the highest one. 7,200 is too big. I don't have a full group of 7,200. So 360. 360 goes into 402 once. leaves me 42. I bring down the 5. 360 is going to go into 425. It looks like that's going to happen once as well. Leaves me 5. And then when we borrow, we have 65. So I have 11 groups of 360. I'm left with 65. What am I going to now do with 65 according to my regrouping process? I'm going to divide 20 into it because this is Mayan. You were thinking Babylonian. It's okay. We're moving around the world and through time, and it's crazy. So 3 times 20 becomes 60. So that means I have 3 groups of 20. And then I'm left with, at the very end, my remainder is 5 units. The last challenge is to write this now in Mayan. And so the way we would do that is you'll have the chart on the test, but each line for them represents 5 and a dot is 1. So the bottom numbers, here's 5. This is 3, 1, 2, 3. And then 11 is 5, 10, 11. There we go. There's my Mayan representation of what we would call 4025. You got time for at least one more. I'm going to give you a couple minutes for exercise 10. Give it a try. 2562. Write that as a Mayan numeral. All right, 2562. We're going to start with 360 because 7,200 is too big place to start. And how many times does 360 go into 2,562? 7. So 7 times 0 is 0. And then we've got 42 and then 21. That's 25. Good choice. Okay, so we're left with 42. So there's 7 of those. I now take the 42. I'm going to go to the next place value, which is 20. And I'm going to divide that into 42, which we can see goes twice and leaves 2 as a remainder. So there's 2 groups of 20, and then there's 2 units left over. And so here's what we have. 2 is just 1 dot, 2 dots. 2 is 1 dot, 2 dots. 7 is 5, 6, 7, like that. And there's your Mayan number. Looks like we got just enough time. Last problem for the day, and then I'll see you Wednesday, is to take the number 10,000 and write it as a Mayan numeral.
If there's like a Chinese system, maybe 0 at the end is assuming.
That's a good question. Write the basket at the end, and if it's anything different, I will let you know on Wednesday. Okay, I will look that up. I'm going to assume that's going to be right because it is a place value system. So the traditional Chinese where they didn't write the 0 at the end was not a place value because they would write the times the 10 or times the 100.
Okay.
So there really wasn't a need for it at the end. But given that this is a place value, I'm going to assume that you would put 2 empty baskets if you're skipping 2 places and everything, because it wouldn't matter. But I will confirm that. Where am I going to start dividing on this problem? Yeah, 10,000 can be grouped into a group of 7,200, so we will start there. So it's just going to go one time, so it's not super interesting. And so 10,000 minus 7,200 leaves me 2,800. So I have one group of 7,200. Now I'll divide 360 into that. And how many times does 360 go into 2,800? Okay, 7, so 0 and 2 and 25. And then that's going to leave me, is that 280? Am I right on that? Yes. And then, yes, when I divide 280 by 20, that is going to go 14 times. It's going to go evenly. So that is 14 groups of 20, 0 units. And so just as I mentioned, I'm going to assume that we're going to use the empty basket at the end, although I understand are asking that because of the traditional Chinese. And so then 14, and then 7, and then 1. And there is our place value number. All right, I understand that this is weird and awkward because your brain is thinking